First of all, thanks a lot for the organization of this seminar series and also to do a dedicated seminar series on drilling. Yeah? This kind of presentation is a kind of perspective study, like it's about future drilling. The past presentations were about past drilling or drillings which have been done already. Yeah? And I'm happy to present with that basically the Afar Dallol Drilling project, which aims to drill in the Afar as a kind of key to unlock the complexity of rifts and rifted margins. And during this presentation, I will mainly focus on the complex sedimentary architecture in these kind of initial rift basins and how this makes the complexity or how this turns the complexity and the sedimentary architecture of rifted margins also quite difficult to understand sometimes. So basically, since the early days of the continental drift theory, the Afar triangle is in the rift community already since a long time a kind of ideal or seen as an ideal field lab where continental breakup and potential oceanic future spreading can be studied in detail. In the Afar, rifting started more or less since Oligocene, Miocene times, and actually you have the action of these three rift zones, the Red Sea Rift, the Gulf of Aden Rift, and the main Ethiopian Rift. The situation at small scale is a bit more complex, and more recently we have been defined the Afar Rift to highlight this complex situation. Basically, the Danakil Depression is the northern portion of the Afar Triangle, bordered to the west by the Nubian Plate, and to the east by this Danakil block or the Danakil Horst. The Danakil Depression is nearly the only exposed area on Earth currently, we would say already, experiencing the point of continental rupture. Wait, I just stuck with my slides transition. Okay, so in the Danakil Depression itself, the crust is relatively thin. In the northern part, certainly, of the Danakil Depression, and here you see a kind of profile where you see this highlighted thin crust. The crust is still continental and it's not yet oceanic crust. And we have been making a kind of model of this crustal structure, and you don't have a lot of magmatic addition to the crust. And this is in contrast a bit to the central Afar. So the Danakil Depression is here in the north, the central Afar. There you have much more magma. You have a kind of magma accommodated extinction, magma compensated thinning under the influence of the Afar hotspot. Extension started to be localized in the Danakil Depression since mid to late Miocene times due to the rotation of this block here, of this microplate here. And then we have this accelerated subsidence rates in the central axis of the Danakil Depression since the Pleistocene, which resulted in the accumulation, basically the deposits of a very high exceptional resolution stratigraphic and sedimentary record. And actually, it's this combination of a very high resolution stratigraphic record with relatively thick, very young scene rift sediments, together with basaltic flows in a close to sea level basin, which makes the Danakil Depression one of the few modern analogs for studying the development of a classic magma-rich rifted margin. I mean, of course, it's a bit a rifted margin session, but I would like to highlight that the Danakil Depression is also a very unique geobioscientific lab. The central Danakil Depression hosts the Dallol protovolcano, where actually hydrothermal fluids and volatiles, rich in carbon, sulfur, result in very active hydrothermal fluid flow, and this is expressed at the surface by a lot of hydrothermal brine pools, sulfuric acidic springs, which becomes very acidic. We have been measuring pH of -1, -2, and also fumaroles. As such, we can say that the surface and the subsurface of the Danakil Depression is experiencing very poly-extreme environmental conditions. And this kind of setting is ideal to determine the physicochemical limits of life. And this has a lot of implications on potential habitability on Earth and or eventually life on other planets. There have been discovered already some very particular extremophiles and haloarchaeota, which opens up new windows also in the origin of life. So with that, also we can study in detail in these kind of extreme settings, and that's what you see a bit here. Here you have the diversity of microbial life. Here you see basically the life-mineral interaction or cell-mineral interaction, cell-mineral fluid interaction, which some mets here and how minerals starts to precipitate. So a lot of questions can tangle into that here, also concerning the understanding of biogeochemical cycles and life in extreme settings, and with that the origin of life and extraterrestrial life. Of course, due to the accelerated subsidence rates, you deposit in a short amount of time a lot of sediments, and this results in a high-resolution sedimentary record, which makes the Danakil depression of this part of the Afar also particularly interesting to study paleoenvironmental change. So it also represents a kind of unique paleoenvironmental archive. And although known as one of the most active rift regions on Earth, and everybody knows this region, Pleistocene and Holocene seam sedimentary rift patterns in the Danakil Depression has been only recently mapped in detail. And here you see one of the results basically of this detailed mapping. All these colors in yellow, brownish, bluish, and purplish, these are all Holocene, Pleistocene sediments. So it's a quite thick package, and we classify them all as scene rift sediments. This allowed us to come up with a kind of synthetic new revised lithostratigraphy for the full Danakil depression. And let's have once have a look at the synthetic profile in the central part of the depression. So running from the margins towards the central part of the Danakil depression. Please note that on this kind of synthetic lithostratigraphic profile, folds and other structural features have not been annotated. We first wanted to understand basically the different succession of different units. And when you look at a west-east profile going from the margins of the depression towards the central part of the basin, the first you have this pre-rift group. I'm not going to talk about that in detail, but then you have this huge package here, which corresponds to the scene rift sediments. You have basically this Bilikia formation, which is consisting of very rich conglomeratic fluvio-lacustrine deposits. On top of that, this has been called also the traditional red bed series. On top of that, you have the Saba formation, which are also conglomerate sandstone siltstones running into the basin, brought into the basin by alluvial fen systems and fluviatile systems. The Saba formation is already Pleistocene in age, while basically the conglomerates you see here belonging to the Bilikia formation, they're mainly Neogene in each. So you go from the Neogene towards the Pleistocene, then you have all this bluish colors here indicated on the synthetic profile. These are limestones, so you have conglomerates intertwining with the limestones. I come back on that later. And then on top of it, so the upper meters of the subsurface, the upper 100 meters of the subsurface in the central part of the basin consists mainly of evaporites. What's below, we don't know, and I will come back on that later also. Let's focus first on this bluish kind of sediments, so these limestones, and then I will take you towards this Dallol formation. So let's first look at this, what we call the Zariga formation. This is mainly exposed, or this kind of formation is mainly exposed at the basin margins. And when you walk across the basin, you see all this kind of whitish sediments plastered against the margins. And when you look more in detail to these whitish sediments, they are full, or they build up by scleractinians, so by corals, which build up huge coral reefs. So you have a kind of coral reef framework fringing the margins, which witness actually open marine conditions or open Red Sea conditions. So open Red Sea conditions during specific time intervals already. So we hadn't only continental sedimentation in the Danakil basin, but also already what we would call from a sedimentary perspective, marine sedimentation. Of course, a detailed picture is a little bit more complex, as corals often co-occur with ooidal and bioclastic grainstones. You see them transitioning in very interesting phases like microbialites, aragonitic crusts, algae layers, monospecific bivalve layers with spherolites, as you see here. And then all those deposits are each time draped by gypsum deposits, which you see here. So this represents always the stage going from a radar open marine, open Red Sea setting towards alternating phase, very restricted conditions with the microbialites coming in and the crusts coming in. And then finally you desiccate the basin with the gypsums even plastering the margins. We have been walking around the basin, having mapped the basin. We have been mapping different coral reef outcrops and associated sediments. And we have been able to distinguish at least 4 distinct coral reef terraces. You see 3 of them exposed here. And we have been able to date all these coral reef terraces. The 2 youngest, there we have very firm dating. So they have been dated at marine isotopic stage 5E for the youngest terrace, which corresponds more or less with 130,000 years. And we have been dating the marine isotopic stage 7 terrace, which corresponds more or less with a period between 210 and 230,000 years ago. Probably we have also the 9 and the 11, so marine isotopic stage 9 and marine isotopic stage 11 terrace. So as such, we can say that the coral reefs have been formed during interglacials when the red sea level was at its highest stance. So it's the combination between uplift of the margins, subsidence of the central part of the basin, and eustatic sea level change, which made that the depression was flooded already 4 times during Pleistocene times. But Valentin Riem will tell you much more about this detailed story of coral elevations and basin dynamics within, I think, 2-3, or within one of the next weeks in the following Rift seminar series. The combination of lithostratigraphy, sedimentary facies analysis, dating, and elevation measurements allowed us to propose this kind of sedimentological model. Here you see 2 of the flooding and desiccation cycles, uplift of the margin, subsidence in more or towards more the central part of the basin, again flooding and again desiccation. This happened, to our opinion, as I said already, 1, 2, 3, 4 times at least, based on the marginal outcrops. So when you walk more towards the central part of the basin, do you have also limestones? What you do see there? So when you look or when you walk from the margins of the Danakil Depression towards the central part of the basin, what you have nowadays, it's an active salt pan, so it looks like this nowadays. When you look into the subsurface, so below this upper surface layer, we have some core sections available, which has been provided by the potash industry, but only from the upper 600 to 700 meter. We don't have any deeper sections. But what you can see already, that most of the facies, this is just the lithostratigraphic column, that most of the facies of the available core sections until a depth of approximately 600 meter in the central part of the basin consists of highlight, indicated by this, on this column, by this purple pinkish colors. Correlation of these central deposits with the marginal deposits allowed to relatively date the base of the core at approximately 130,000 years. This would mean that the upper 625 meter of the core records the last more or less 130,000 years, which is a very high sedimentation rates, which make this core also as being very valuable for paleoenvironmental and paleoclimatic reconstructions. And currently we're trying to detangle all these potential annual cycles you do see in this highlight section. So you could start to count them, and with that have very high constraints on sedimentation rates, which can be then linked to the basin story, where you can start also to calculate the subsidence rate and compare this with the uplift rates at the margins. Moreover, if 4 flooding cycles produced a similar amount of sediments, you would fill potentially the basin with 2 kilometers of sediments where you have a lot of evaporites intertwined with more siliciclastic sediments and potential also some marls. And with that, we could question if the Danakil Basin is also a very important, very recent active salt giant. However, of course, this is hypothetical because we don't have any core data below this upper 600 meter. We basically only have core data till here, and we have no clue what's happening below. And this basically led us to propose a new drilling project, add-on Afar Dallol Drilling, where we would like to drill basically below this upper 600 meter, upper 600 to 700 meter. We have seismic data. We have been analyzing the seismic data. We think we have a repetition of these sedimentary units at least 4 times, and we would like to cover that, covering the full Sin Rift sedimentary record and potentially some of the basement, basically. So the add-on project aims at drilling in the Sin Rift sediments in the Danakil Depression, and this unique kind of sedimentary archive will provide us with the necessary core and downhole data to unravel this complex paleoenvironmental change in the Rift Basin, provide us with the stratigraphic constraints to understand then other different angles of the project, for example, to understand incipient and intermittent basin dynamics through very probably punctuated volcanotectonic events in a rift transitioning from continental rifting towards seafloor spreading, and probably adjacent rifted margin development. So we really think you have this very punctuated events in time, so not really gradual, but very fast change and then a quiet period. But that has to be proven, of course. Then also, this will allow us to give a sedimentary record to test the origin and limits of life in the deep biosphere under poly-extreme conditions. We would be able to test or to understand better fluid flow and fluid sediment interaction in a very active hydrothermal system. And ultimately, we would like to use the hole, to use the drilling site to develop a kind of downhole Earth observatory to improve hazards and risks or monitoring basically earthquakes, gas fluid flux, ground motion, and so on. So that's the idea of keeping the hole all longer term open also. We have been doing several workshops trying to frame the project with all the different angles of view. The last workshop we have been doing in Addis Ababa in Ethiopia in August 23, and we have been submitting now a full proposal, which is currently under evaluation by ICDP. If you're ever interested to participate, stay tuned and do not hesitate to stay in touch. And based on the workshop outcome, we have been digging a little bit further, and the next phase, what we're doing is to walk from add-on to rift off. So we're compiling different core sections in the central northern Red Sea, southern Red Sea, and Gulf of Aden, in order to compare the records which we have already in the Afar with the Pleistocene, Holocene records of those areas. Of course, it's difficult to go towards these areas, and ideally you would need some new drillings in those areas. But we have been looking at the available drillings using a kind of legacy approach. So old DSDP core records, we have been describing them in April as a kind of preliminary study. And now we would like also to propose a new proposal, a new Sparks proposal within the new IUDP program, basically to look at these available core sections. So also if you would be interested in that, to cooperate on that, do not hesitate also to drop a message. So this is a bit the philosophy of the add-on project. Thanks a lot for listening. Also thanks to the full add-on team, the full Sirena and Connect teams. These projects have been also seed funded by the Swiss National Science Foundation. And we have an active bilateral exchange program between Switzerland and Ethiopia, where we actively do research together. So thanks a lot.
Thanks, Anneleen. That was fabulous. So feel free to start raising your hand for questions. I saw in the chat, Joanne, you have an initial question, so feel free to ask.
Oh, yes. Thank you. What a great presentation. I wondered if you see in the seismic data or any other observations mobility of the evaporates and the salts. Like, do you expect this to be a big concern in terms of understanding the full history of the basin?
Yeah, very good question. So we have been comparing different seismic sections. We're currently writing the data up into publication. Some of the units we can really correlate across the basin. And indeed, when you come closer towards the Dallol, what's called a volcano between brackets, there you see active salt movement also. And this we observe also on the seismics. So there you see the salt movement on the one hand, and you see also gas and fluids moving up. So you have sometimes blanking of your seismic signal, of course. So it's not always easy to interpret all the structures, but there you see it clearly. When you go a little bit more away from this salt volcano, or from this Dallol volcano, there you see less diapirs, for example, so salt diapirs. This is less visible on the seismic section. So there we really see a kind of correlation between all the units. But yes, you have salt movement very close to the Dallol volcano.
Okay, thanks. Any further questions? Okay, Anneleen, I have a question. What's the sort of magnitude of uplift of these coral terraces, and sort of what would the sort of inferred uplift rates be?
Yes, so the uplift rates of the coral reef terraces are in terms of millimeter per year, basically. So it depends where you are in the basin, and I think Valentin would like to talk much more about that. But the basin is kind of fragmented in different subbasins. So in the southern part of the basin, you nearly don't have any uplift of the coral reef terraces. They are really in stratigraphic order. And when you go towards the northern part of the basin, there we see, basically, I just go back to the slides. So in the northern part of the Danakil Depression, there you really see that the oldest terraces are on top of the youngest terraces. I didn't explain that during the presentation. And there you have also much higher uplift rates during marine isotopic stage 7 and 5 than from 5 till nowadays. But I'm talking about 0.01 millimeter a year, basically.
Okay, thanks. So I see in the chat, Maya has a question. If you wanted to say the question, or else I can read it out. Okay, I'll read it out. So, Anneleen, there's a question from Maya. Say, what are the biggest obstacles for deep drilling in the area?
Well, yeah, that's a good question. So, I mean, there are logistical issues because you can't drill during the full year. So the depression is also flooded during the humid period. So you should do the drilling during a very constrained time period. So this is a big challenge. And then you also have quite high temperatures. So you work under quite harsh conditions for the drilling. So I think this turns it challenging in some way. On the other hand, we have targeted drill sites where we hope the geothermal gradient is not too high. And with that, wouldn't encounter too crazy temperatures. So we envision to drill till a temperature of basically maximum 100 degrees. But